Given an array nums and a window size k, return the maximum in each sliding window of size k. For example, here they have given this nums array as this 1, 3, -1, -3, all these things. K given as 3. Then output is this. Okay. It's like this question blew my mind in the first time. Given an array and a window size k, find the maximum in each sliding window. And no, we can't sort every time. It has to be super fast. So let's solve lead code 239 with a clean deque trick. Intuition is about we are sliding a window of size k across the array. At every step, we want to know what's the biggest element in that window. So brute force way, loop inside every window, that is big O of n into k. That's too slow. So we use deque, that is double-ended QE. So to keep track of indices of elements in a way that the front of that deque always gives us the max. How? As we move forward, we remove smaller elements from the back. We remove out of window elements from the front. And we always know that the maximum of the current window is at the front of the deque. That's the trick. So if we see this code, this deque stores the indices. And next, this removes the out of the window indices, this loop. Next, like it's like remove indices whose corresponding values are less than I. This does that. And next adds the index to this deque, then adds maximum for the current window to result only after the first is k minus 1, that is only it is greater than the k minus 1. If we say this line by line, first we use a deque to store the indices, not the values, because we want to know if an index is out of the window or not. Compare current value with the value at indices. Next, loop each element one by one. Then afterwards, step 1 is to remove elements out of the current window. We need to remove the elements out of the current window. In front of the deque is outside the window, that is index is less than or equals to I minus k. Okay. Next, we remove it. Next, while condition is about step 2. It is like remove all the smaller elements from the back of the deque. Remove all the smaller elements from the back of the deque. Why? Because they can never be the maximum in the future windows. So we don't need them. So deque only holds useful candidates for the maximum. Then it will be pushing back into the deque. Step 3 is about add the current index to the deque. It must be the max in this future for the future windows. Okay. Next, it gives that result. To show that thing, after that, we have filled at least k elements. We can start adding the maximum of the current window to the result. Then the front of the deque always holds the index of the maximum. For example, if we go through this example, okay, if we go through this example, here at index 0, we have 1. Okay, so deque is like stores a 0. Next, 0 index. Next, here we have at index 1, we have 3. That is greater than 0. Then pop 0. Okay. Next, it also takes that. Next, it is -1. -1, at -1, it will be storing 1 comma 2. It will be storing 1 comma 2. Next, at index 3, we have -3. Then it will be storing, it will be popping 1. And 1, 2, 3. 1, 2, 3 is the index it has stored. Then it will be popping 1, right? After popping 1, at position 4, we'll be having 5. So it has the 4. That is a pop smaller. Next, at index 5, we have value 3. So at 3, we'll be having 4 comma 5 because we are considering 3 also. Okay. Next, at index 6, we'll be having 6. So pop all the smallest because this is the larger one. This is the larger one. So 6 is the larger. Remaining all will be popping up. We'll be left with only 6 index. Then we'll be going to 7. Then while we are seeing 7, 7 is the larger one, but k is given as 3. So we'll be considering as 3, 6, 7. Okay. So time and space complexities are like time complexity is big O of n, space complexity is big O of k. Time complexity big O of n because every element is pushed and popped at most once from the deque. So this question is a real DSA gem. It teaches you how to think in Windows and how to use deque smartly to avoid brute force. Once you get this trick, you will solve any maximum in window problem in seconds. This was our last episode in the arrays DSA hard series, and so if you have made it here, you have grown a lot. Comment I survived the DSA hard array series. It has helped, and I'll see you in the next chapter. Thank you so much for watching. Hope you have understood this logic.